Can you help me to mute people? And then we check.
I can't. I'm not host.
Yes, you are. Okay, I think we might be live. Okay, we are live.
Okay, welcome everybody to this Latin American webinar of physics. Today is very interesting and we are very enthusiastic and very excited about because we are arriving to our 100th webinar from this cycle that we started 5 years ago. So we are gonna be celebrating all these days and mostly the next 6 months with very impressive webinars, especially this occasion, because today we have, for this special occasion, that is our 100th webinar, we have Professor Reiner from the MIT and Louisiana State University, that he's going to talk about the future of gravitational waves. So before to Professor Reiner start with his webinar, let me tell you about his work, why he's so known and he's so famous. Professor Rai Weiss, that I just said, is emeritus professor at the Massachusetts Institute of Technology and adjunct professor at the Louisiana State University. He is known for his pioneering measurement of the spectrum of the cosmic microwave background radiation, his invention for the monolithic silicon bolometer, and the laser interferometer gravitational wave detector, and his roles as co-founder and the intellectual leader of both the COBE project and the LIGO project. COBE for the microwave background radiation measurement, and LIGO from the gravitational wave detection. He has received numerous scientific and group achievement awards from NASA and MIT Excellence in Teaching Awards, the John Simon Guggenheim Memorial Foundation Fellowship, the National Spacecraft Science Award, the Médaille de Lyon Observatory de Nice, the Gruber Cosmology Prize, and the Einstein Prize of the American Physical Society. And of course, and in 2017, Professor Weiss, he was awarded the Nobel Prize in Physics along Kip Thorne and Rai Weiss for the decisive contributions to the LIGO detector and the observation of the gravitational wave. So we are super happy to have Professor Reiner here with us, and he will talk about the gravitational wave and what is the future and why it's so exciting to learn about, and to you people that are following us in YouTube and during all this time about the gravitational wave. Professor Reiner, if you want, you can, I don't know, we are so happy with having you here.
Well, thank you very much. I don't know how I should start. I'm going to start by sharing the screen, if you don't mind.
Yes,
yeah, that would be good.
That's probably the right thing to do. And now I have to make sure I hit the right thing. Okay, there we go. First of all, I just want to thank Gabi for inviting me indirectly, and then all of you guys for making such a big effort. I mean, I didn't realize you had such a nice thing like this, Latin American webinars is a very good idea. I wish we did things like that in many parts of the world, and especially in the United States also. It's a nice idea. Anyway, what I'm going to tell you about is something Gabi could tell you about better, but she's not here right now. And so is a little bit of the story about what's behind having made a discovery of gravitational waves, how it's done. And you may have heard that before from others, but I think it's worthwhile repeating it. And then I'll tell you a little bit about what things have been discovered and a little bit about the future. Really, the title of the talk is sort of the very end of what I'm going to tell you about. So let me start with the most elementary thing I know how to do. And let's get this going. Oh, dear. And that is to begin with things that most of you know about. I mean, by the way, this pointer, I'm just hoping that you can see the thing. I have Newton being encircled by my pointer. Okay.
Yes,
you can see that. Okay, excellent.
Yeah.
Well, the equation at the bottom, many of you know, it's Newton's wonderful sort of direct connection of what has been experienced with gravity and mathematics. And it says that the force of gravity, that's the force of gravity on two masses, that's one of them, and that's another, is proportional to some constant, which is not terribly important. It's a number, but it goes as the 1 over the square of the distance between objects. And this simple relationship explains almost everything we have ever experienced with gravity. It explains the tides. It explains how the Earth and the sun move. It and it explains spacecraft, but it doesn't really work at the very most precise level. And for example, one of the things it doesn't have is a way for information to go from one place in a gravitational field to another. And also some other problems, which we'll get to as we go along. But, and the other one is that I don't know how many of you have GPS receivers on your cell phones, but GPS wouldn't work at all if it was just for that relationship in gravity. You need something more complicated. And this was Einstein, who had a very different viewpoint. Unfortunately, this is a very old picture of Einstein. He invented the theory of gravity in 1915. He didn't look quite that old. But the equation he came up with is deceptively simple looking, but enormously complicated to work with. And let me tell you what it says. It says that the geometry of space and time, that's space and time, the geometry, how you measure space, how you measure time, is somehow dependent on the distribution of matter and energy in that space. In other words, matter and energy in the space make the geometry of space and time. And I'll give you a little feeling for that with a picture that is, it's almost right. It's not beautiful, but I don't know how many of you know what a jungle gym is. In New York, I come from New York, and all the kids in the park play in jungle gyms. These are parallel bars, and kids jump around inside them. And what is here is a cut through a jungle gym. Here are all the bars, and they're all nicely spaced in a regular way. And what's been put into this picture is you've made a cut through it. It's a two-dimensional cut. You put the sun into the picture, and here's the Earth right there. And you notice something interesting. The sun has made a distortion in the space. It's curved the space. The things that were straight lines no longer are straight lines. And the Earth has done the same little thing. It's not as big as the sun, and so it's more gentle, but it's made a little dimple in space. Now, what is not shown in that picture is what it's done to time. I'll just have to explain that. It would have been quite complicated to draw that all in. But suppose you're out here where everything is quite flat, and you put clocks everywhere. Everywhere there are intersections of bars, and you would find a very interesting thing. If you did that, and we do that every day, we put clocks everywhere, people wear them. They all read the same time if they're set right. And what happens in this space is as you move, if you have clocks that are going into this region, which has been distorted in space, it turns out time has also been distorted. In other words, the clocks that are near the sun, they go a little more slowly than the clocks that are far away from the sun. That's also true on the Earth. And their clocks go a little more slowly here than far away. So there's a distortion of both space and time. And the way gravity now operates, and this is a wonderful phrase that John Wheeler put, he says that space tells matter how to move, and matter tells space how to deform. And there is no more a gravitational force, it's gone. And it's a beautiful theory, extremely complicated to work with. And unfortunately, or fortunately for everybody, it gives the right answers, whereas Newton's theory doesn't anymore when you get to look at very precise things. Now, the first thing is a gravitational wave. I'll explain to you what a gravitational wave is. It's a picture right in front of you right now. What they were part of Einstein's thinking in 1916, he wrote a first paper about them. Well, it's in a paper that he has other things in, but in 1918, because he made a mistake in this paper, he had to do it all over again. He gets it right. And what they are, the sources of gravitational waves are accelerated masses that are accelerated. You accelerate a mass and you generate a gravitational wave. But it can't be every kind of motion. It has to be a non-spherically symmetric motion, a motion that isn't like a balloon that expands. It has to be something that has some curve, that has some asymmetry in it. Like, for example, two objects going around each other, or two things smashing into each other. They make gravitational waves. And the kinematics, which is now started, I don't know how that started, but it's doing it good, is that they propagate at the speed of light. And they are waves that do all their stuff perpendicular to the direction in which they're moving. In other words, they're called transverse waves. And here's a picture of one. And what you're doing, these dots are places in space, and you are sitting right here at that little red square where nothing moves. And you'll notice the gravitational waves, by the way, in this picture are coming at you or you're going into the screen. And you'll notice two interesting things about the picture. One of them is that along one dimension, let's say the horizontal dimension, there's expansion, while along the vertical direction, there's contraction. And that keeps flipping back and forth. I hope you can see that. The other thing is that if you're standing here, the dots that are moving the most are the ones that are furthest away from you. The ones that are close to you, like that one, doesn't move much. And this one moves a lot. That's also true in this dimension. And what kind of a motion is that? It's a strain. In other words, it's a property that it's the change in length, or the displacement of an object is proportional to this. Let's say you compare this, the one on the out here, and the other one out over there. Their separation is changing a lot, where the two ones in here are not changing very much. So the separation of the objects is proportional to this. The change in position of the objects is proportional to their separation. In other words, if you're doing this mathematically, if you say delta L is the change, and you divide that by L, which is their separation, that's the same along the horizontal direction and with an opposite sign in the vertical direction. But all along, it's very much like if you took a rubber band and pulled a rubber band, you marked it, and another friend of yours made little marks on the rubber band, and you pull it, and you notice what's going on. The spacing of all the marks you made, it gets different. It looks very much like what's going on in this picture. Okay, so what are gravitational waves? They cause distortions that are in opposite directions, in two perpendicular directions to the wave's motion, and they make strains in space. And that was first person to think about trying to measure such a thing was Joseph Weber. He was a physicist and engineer at the University of Maryland, and he was hoping to have a following thing: a gravitational wave come and stretch this big piece of metal and stretch it along. It stretches it this way and contracts it along the radial direction. And he was hoping to put little sensors, which he did, on this. You can see them on there, that would try to measure that motion. And then he would put this in a big tank and close it up, and so nothing would disturb it. And he tried to look for gravitational waves. He thought he discovered them, but to his misfortune, it turned out they were not. A lot of other people then looked, and they didn't see they didn't see it. In other words, it was an interesting idea. He was the first to think about this, but unfortunately, the ideas he had didn't work. And the reason we now know it doesn't work is because the strains that he was able to measure were much, much too large compared to what nature actually provides. So here's a system that actually is working in LIGO. And here, this is a picture of a very simple, primitive picture of a gravitational wave will come down on this thing. There's a laser here in this. Doesn't look like a laser, but it's a laser. And here's a beam splitter. That's the thing that divides light. So laser light will come out, hit this, and half of the light will go to that mirror over here to the left, come back, go through it, and go to a photodetector, which is over here. The other half of the light will go through it and hit that mirror, come back again, recombine, and go to the photo. Some will go back to the laser. Now, I'll start this up and you'll see what happens. Let me see if I can get it going. Yeah. The laser light is red. Wherever there's laser light, there's red. And the wiggly thing in the light is the electric field of the light. And you'll notice when these two paths, which are to the two mirrors, are equal, there is no light going to the photodetector. The two waves cancel each other perfectly. There's no red over here. Nothing goes to the photo. Now, down comes a gravitational wave, which stretches one of these and contracts the other. And now there is light going to the photodetector. And that is the basis of the entire measurement that LIGO makes. It's nothing more than that. The trouble is, it's a very, very tiny motion. And that comes next. So That's the basis of the interferometer. That device is an interferometer. Now, here's a very famous man in our field, Kip Thorne, taken probably when he was a young man. He had a crazy symbol. And he had already done calculations of how big a gravitational wave might be. That's the strain, H, or that's expression of delta L divided by L. And the number that he and others, but he did most of the early work on that, showed that if you were going to detect gravitational waves, you had to make an instrument that would measure 10 to the minus 21 strain. That's enormously small. And in a 4-kilometer system, like what LIGO is, L is 4 kilometers, the change in length at the ends would only be about 4 times 10 to the minus 18 meters, which is something like 1,000th the size of a nucleus. And so there were 2 very hard things to do. And these were the things that took Gabi and a lot of other people a long, long time. They were dealing with wavelengths of light as the measurement sticks, and they're 10 to the minus 12 of a, you know, this is 1 part in 10 to 12 of a wavelength of light. That's 1 billionth in a British billionth. And the vibrations of the Earth were so much bigger than that by a factor of 10 to the 12 also. So you had to deal with all sorts of junk, motions of the Earth, motions of things that caused the mirrors to wiggle, that you had to solve those problems. And this is the instrument that actually was then used ultimately to do this. And I won't go through the entire thing, but the part that you will recognize is the laser. And there's the beam splitter. And over here is a mirror, test mass mirror, and the same thing over here. And there's the photodetector. And what's new in this picture are some new mirrors. And these new mirrors make the light bounce back and forth many times. And here, many, many times, sampling that mirror a lot. And then there are other mirrors that are used, which are partial mirrors, which are used to build up the light inside. And I won't go into that unless you ask me about it. This will build up the light from the laser. It's called the power recycling mirror. And this will build up the signal. It's called the signal recycling mirror. All these tricks were necessary to make this measurement. And here is sort of a picture of the kind of things that are in the way of making the measurement. And what you see here is a graph where here is the spectrum, or it's the measurement of the amount of strain at each frequency. So it's a spectrum of the strain versus the frequency of the signal. So here's 10 hertz, 100 hertz, kilohertz, and so forth. And the initial LIGO that we built, the very first LIGO we built, worked in a regime where you can see in here, this was the region which was clear in this band right there. And these are different things that kept you from being able to make the measurement. One of them was that the light from the laser, as seen at the photodetector, was granular. It was quantized. And the same here, the other part that was very important is that you could only shield the ground motion so much. All this is all due to the ground motion, anything. And then there's a little piece right here, which is due to the fact that we were operating this instrument at room temperature, not at very cold temperatures. That's called suspension thermal noise. And there's some other noises in here, which later became important. But the one that here is sort of the limit in this thing is there is a limit, which is called the real quantum limit for this, is the granularity of the light, the phase noise in the light, against the fact that you're dealing with photons that are pushing on the mirror, and the noise in the pushing on the mirror, the light itself presses on the mirror, and that makes a noise, which is especially important at low frequencies. And then let's not go through all these other things, but this was our initial challenge. And well, okay, we set up a whole bunch. There are, and this is pretty much from the beginning. These are now the different places in the world where people set up detectors like this. The LIGO detectors are one in Louisiana, where Gabi is, and then one in the northwestern part of the United States. And these were the LIGO detectors. There was a smaller detector in Germany called Geo 600. That means it was 600 meters long. These were 4 kilometers long. And Virgo, which is a detector in Italy, And since I'm only going to show you this once, there's a new detector that's just started operating in Japan called Kagra. And there's a detector that's just being built called LIGO India. So that's the world's collection of gravitational wave detectors well, within the next probably 5 years. And the ones I'm going to be concentrating on are the American ones right here. And here's what the American systems look like. You're looking down here on the site in Louisiana, and that's the site in Pacific Northwest. And the light travels in a vacuum tube inside these concrete covers. This happens to be Louisiana. And here's that big evacuated tube that carries the laser light. And here are people working like in a laboratory, adjusting the lasers and adjusting mirrors. And here's the control room for the system. And here are people learning how to control the detector. So it's big science, but it's not huge science. There's still people who know most of what's going on in different parts of the experiment. And so here's what happened in the first go with LIGO. There's a picture. It just shows you the kind of work that had to be done. And you can see when it started. In this picture, it started about 2001, and it quits at around 2005. And here is the sensitivity. This is now that strain displacement sensitivity as a spectrum. And here's the frequencies down here again. And here is sort of the best frequency, really around 100 hertz. And here, when we started, these are orders of magnitude, each one of these, powers of 10, 10, 10, 10, 10. So in 2001, the first detector we put in the LIGO facilities was up here. And we kept working on it. And at the end of the first detector, we were down here, very close to the theoretical limit. The theoretical limit is those bars, and this one, you can see a little bit. We missed the theoretical limit at very low frequencies. But there it is, it goes, it blends with all the others. And at this point, we're very proud of the fact that we were not happy about this, but we were very proud that we understood why we had not made a detection. In other words, we understood the instrument well enough that there were no hidden gravitational waves that we could detect at the sensitivity of this red line down here. We just were very sure there were no gravitational waves that we could find. And we went and said, look, we know how to build a better detector, and let us do that. And we'll put that into the same facility. And that's what we did. And that better detector had big changes that were made in, and I won't go through these in very great detail, but that made changes in how we suspended the mirrors. For example, whereas in initial LIGO, we had only one pendulum, this is 1, 2, 3, 4 pendulum, all in series. And this is this very precious mirror, which we're trying to isolate and is going to move with the gravitational wave. On top of that, we built a whole active system. Here's that pendulum system hanging from a box, big box, that is full of seismometers and accelerometers, and which is held at a fixed point in inertial space. And from that, we had, by tricks, like pushing on these systems with forces that eliminate the ground noise by measuring it. Those are called active vibration systems, isolation systems. And those might be useful to you guys if you're building very careful experiments. That's why I want to show you this. And from that, you now hang this very good pendulum system. And with these two big changes, we actually made a detection. And here it is. The very first detection we made was, and this is a picture of, so you can get an idea of the scales. This is the strain in units of 10 to the minus 21. So here's 0, there's 1 times 10 to the minus 21. And this is time. So at 0.3 seconds to 0.45 seconds. And this is junk. This is the signal in Livingston, in Louisiana. This is junk. And then slowly something builds up in it. And after a little bit, it gets bigger and bigger. And this is junk again out here. So here's what happened in Hanford. It's very much the same. It's junk, but then it builds up, and the two signals are put on top of each other. I think you can show it here. And you'll see that they are not identical. They can't be in this region where it's all noise, but they became more and more similar to each other when you get out in this region where there really is a signal. And the important thing we already knew at that time when we that the signal came into Louisiana first by about 7 milliseconds. And then it went through the Earth and hit Hanford in Washington. And this is what happens when you move the blue signal, the signal, one signal with respect to the other by about 7 milliseconds. Now, what was that? Before I say that, there's another way to, if you have your audio on, and probably you do, there's another way to listen to the signal. This is what, if you had earphones at the site, you would have heard this. And let me just see, what's plotted here is, instead of strain amplitude, what it is the amount of signal at each frequency. That's the actual spectrum of the time series. And there is the time series right there. And then the time is on the bottom. And what the strength of the signal is this. The brighter it is, the stronger it is. And that's the two signals, one at Hanford, the other one at Livingston. So let me play it for you. That's not very impressive, that boop, boop, but that's what that chirp at the end is. And we can trick it up a little bit so you can hear it better. Okay, so that was the very first thing we detected. Now, what was it? And we had expected other things, but early days, people like Kip Thorne, the person I showed you the picture of, had thought of detecting gravitational waves from black holes. That's something that Einstein's theory predicted. Is when matter gets so dense in a star, for example, and that the mass of the star and the material in the star is so dense. It says, in other words, the large amount of matter is compressed into a tiny volume. And then even light can't get away from it. The light gets pulled back by the gravitational curvature, just gets pulled back into the black hole. And now what's this picture of is not artist's conception. This is a very, really elegant numerical calculation you're going to see in a minute of two black holes going around each other. And now on the very bottom of the picture is the waveform, the time series. And what we're going to see is what's going on in that system. So let me start this. The two black dots are the black holes. We're going to look down on a two-dimensional surface in a minute, much like the jungle gym I showed you in the first picture. And here's what's happened. Here are the two black holes. You can see the curvature that they've generated in the space is enormous. And the time is now represented by colors. Where it's green, the time is running pretty quickly. Where it's red, it's slow. And when it gets black, it has absolutely stopped. And then the little bars are effectively the stresses, in fact, the strains that are in the space. And you'll see the time of this collision. They're getting closer and closer. And at some point, we'll slow this down so you can see really what's going on here. We'll slow it down now. And you can see these two black holes have caused an unbelievable amount of distress and curvature in that space. Their time is stopped in the bottom of the hole. And here the two black holes coalesce into a new black hole. And things calm down. And the waves that you see going away from this hole are the gravitational waves that we detect. And that is a numerical computation done on a computer, and which matches quite well, in fact, very well, the thing that was seen in the signal. And so that became, we were able to announce that in February of 2016. And I happened to be in New York in, maybe March. And this is what I saw in the New York City subway. It's just for fun. Here is an advertisement on the wall. I mean, I can see the impact that this discovery had. It says, scientists found gravitational waves in outer space. If only it were that easy to find an apartment in New York City with a walk-in closet. And so this has sort of hit the public imagination. And over here is a New Yorker cartoon. And two birds standing there talking to each other. And one says, was that you I heard just now, or was it two black holes colliding? The same thing you heard just a few minutes ago in that sound transcription. So anyway, it's kind of fun, but it was an important discovery for people everywhere because they knew about Einstein, and a lot of kids and people have learned about black holes in comic books and other places. So it wasn't totally strange. So it turns out very quickly, so we began this. This is a picture of this, the same thing we saw before, now cleaned up a little bit. This is strain up and down, and again, the time series over here. And this is the one we've been talking about. And this tells you that that was seen on September 14th of 2015. Well, it turns out, and what was the masses associated with that? Well, there were 36 solar masses in one of those and 29 in another. And 3 solar masses were lost into gravitational waves. And that's spectacular. That much energy goes out. And it's one of the most impressive explosions in the history of the universe. It happens all the time, but when it happens, it's brighter than the whole universe for a moment in energy. You don't see it. Gravitational waves is the way they see it, or you see it with quotation marks. Well, it turns out, very shortly after that, and this is now on October 12th of that same year, we saw a different one. We weren't so sure of this one. It had smaller masses and it had lost less energy. But the one we were more sure of is this one that came one day after Christmas. And when that happened, most of us who were in the collaboration began to believe this one. In other words, there was a lot of skepticism about this. There'd been that bad history with Joe Weber. And here we had spent a lot of time and a lot of money. We had to be absolutely right that what we were detecting were gravitational waves. And many of us felt uncomfortable, and certainly I did, that we had only one gravitational wave source. But now we had at least 2 that we were sure of. And then it snowballed. We got more and more of them. And the first really new thing that happened pretty quickly was that the detector in Italy, the Virgo detector, had come on the air, and it also saw a black hole event. This happened in 2017 on August 14th, and you can see here the time series again for the LIGO. That's Hanford, that's Livingston, and then there is a little smudge in here, right there, which they were not as sensitive as we were. That's because they hadn't had as much experience as we had, but they were seeing a signal also. And so this was very important. The reason was, first of all, another group had seen this. This is great. On top of that, it allowed us to do something which became even more important later on. And that is, with 2 detectors, you can tell where the source might be. Like the first one we saw, I told you it hit the southern detector first, and 7 milliseconds later, it hit the northwest detector. That told you right away that it was somewhere in the southern sky. But you can do better than that. And when you have 2 detectors, you can draw a big circle on the sky, and you can say that the source had to be somewhere on that circle, just from the timing differences. You don't see anything. It's the fact that you're timing these pulses as they come in, and you see differences in the time. Well, it turns out with 3 detectors, you get 2 great circles on the sky, not just one, with 3 of them. And so now you can pin down better where the detector was. So here would have been the place where LIGO, this is a sky picture, this picture. And here's where LIGO alone would have said it had to be. And now you add Virgo to it, and it narrows the thing down quite nicely. Still not good enough for an astronomer. And this is 2 versions of the same estimate. So 3 detectors had seen this. And the important point is it allowed people to localize the position of the source better than before. And since then, this is now a picture that was drawn, not more than a couple of months ago. This is the collection of, it looks a little crazy, but this is a collection of black holes that people had seen before, the ones on the bottom. This is the mass of the black hole in solar masses. So here's 2 solar masses, 40, 160 solar masses way up there. And this axis is just a way of, I don't know, it's just a way of separating them all out. And so here is we've now seen, this is a lot of discussion about this pair of black holes when they collided, making this thing. That's the biggest mass black hole we've seen. And it turns out that it's now engendered, this field has become a field not only of physics, but has become a field of astronomy. And why? Because, well, now you want to figure out how does nature decide to make so many different sizes of black holes? How does it do it? And people thought they had a pretty good idea about that when they only first saw these little ones. And then they thought, well, it was still okay to, we understood things pretty well when you got up to about this level, everything down here. But when you get such big ones, none of the theories that we had for how stars make black holes really were effective or not. And this has caused people to start thinking about all sorts of different ways that black holes can be made. And some of it's unanswered. For example, there are 3 ways that we know. One way is to have a star get heavy and get to the point where its internal furnaces turn off. You know, it doesn't make so much heat, and it contracts like crazy, and it makes a supernova, and then leaves kernels. And usually it could be neutron stars, and we'll talk about that in a minute, or it could be a black hole. And that's the way everybody always thought that's the way black holes were made. And it may be right. On the other hand, pairs of black holes is what we're talking about here. How did they get together? Well, there must be supernova which make 2 black holes. It's getting a little hairier. So then there are other ideas. And other ideas, there are places in our galaxy as well as in others where you have many, many stars living all together in what's called a globular cluster. And there it would be a different kind of formation. It would be stars smashing into each other, building a black hole that way, and then the black holes beginning to smash into each other. That may be. It could also be that there are black holes from the very earliest moments of the universe without having had any stars. That's a pretty radical idea, and we thought it was a pretty much dead idea until we began to see so many of these things. And that's a nice challenge. What possible, how many primordial black holes are there? It's already known they can't be the source of the dark matter, but they could be a little bit of it. They're just, the dark matter is just too smooth to be all black holes, but that's a long story. So this is the story with black holes. We have opened a new field here. It's called black hole astronomy, and that will go on for a while. We're learning a tremendous amount about these holes. And you can ask me about what other things there are, but let me go on to a thing which is a different source entirely. And this was a source that was discovered also in 2017 in the summer. It was in August. That month was very productive for gravitational waves. And what was seen in our instrument was a thing that made this trace down here. This time scale is entirely different. These are time scales that are where this is about from here to there is 2 seconds. So this is a fairly long thing. This thing that makes this chirp, which we'll hear in a minute, lasts about 10 seconds before it gets to the point where we can't detect it anymore. Let me play it for you so you can hear it. Sorry, didn't work it. I got to go back and try to make this go. There we go. They're kind of entirely different. And what this is, and we will talk about a lot now, is 2 neutron stars, which are less heavy and less dense, of course, than a black hole. And they're made up of just nuclear material, neutrons. And they were discovered as pulsars many, many years ago. And they have made a huge difference in astronomy. They spin, they keep very good time, a whole bunch of nice things that pulsars do. But they are stars that somehow were formed in the collapse of a supernova. That one we're very sure of. And so it turns out that the formation of these pair of black holes that we see by gravitational waves turns out it will also make electromagnetic things you could see with electromagnetic telescopes. And this was the situation that happened. Here above this is the time series from the Fermi satellite, which is a gamma ray telescope. And this is noise, noise, noise. And at the moment when this collision finally happened in our data, not quite at that moment, about 7 seconds later, there was this gamma ray pulse peak. And that also happened in another instrument on the Fermi satellite, which was a different kind of instrument, different energy. This is 10 to 50 kilovolts gamma rays. This is 50 to 300 kilovolts. It's probably better seen at the high energies. And also in another instrument on a completely different satellite. That a little more dubious. So this was a big deal because what we now had is we had a lot of stuff going. We had the electromagnetic detection, which was a confirmation of everything. And we had it within 2 seconds, call it, of the gravitational wave hitting the Earth. It told us something really absolutely amazing. It said, look, whatever went on at that neutron source, and we'll talk a little more about that in a second, but these things we now began to realize came from a source that was about 130 million light years away. Maybe I should show you that. Yeah, let's talk about that before I tell you this stunning thing. It is a source that was a galaxy which people knew about, and let me go back to what would be the gravitational wave, and I'll get back to the story I want to tell you about the short time difference between the gravitational wave and the electromagnetic one. But let's finish the localization. So here is the region. It's again a sky map right there. And the localization as done by LIGO would be the big banana right here. And the localization with Virgo, which did not see it, but it happened to be in a place where there was a null, a zero in the antenna pattern of their detectors. So we assumed it was there because they should have seen it. And doing that gave us an error bar that was only about as big as that. Here's the error bar that's associated with the Fermi satellite. So what happened is very shortly after this happened, LIGO sent out a telegram, Fermi satellites sent out telegrams. People on the ground got these telegrams and they trained their telescopes on that region. And lo and behold, this is what they found. People have been looking there before. Here's a galaxy down here on the right, which has these stars that are in our own galaxy. But this fuzzy thing is a galaxy. That told us where this happened. It's an NG, it has a name, NGC 4493. God knows, I don't know anything about that, but that we know where that is from radio astronomy. It's about 130 million light years away. And so this was taken about 20 days. This picture was taken about 20 days before the event. And here's a picture taken about 10 hours after the event. And you'll notice all the stars are in the same places, that one and that one, this one and that one, but there's a new thing right there at that point right there. And that is that supernova or collision of the two neutron stars. And it's not exactly in the galaxy. It's a little bit outside of it. Well, that's been predicted as the most likely place for these neutron stars to form in the first place. So that was a big, big deal. Now people could see this thing with ordinary telescopes, and boy, could you learn a lot of stuff. And a whole new age of astronomy was started. It's called multi-messenger astronomy. Namely, you use gravitational waves, you use X-rays, you use radio waves, infrared, ultraviolet, and the more different channels you have, the more you will learn about the system. And that's become very, very productive because a gravitational wave alone would have not been as productive as what follows. But now I can tell you the story I was going to tell you. And that is knowing where that galaxy is at 130 million light years away, and going back to the fact that these two signals, I'm going back to the other slide, are only about 2 seconds apart. This one, this signal right there, and the one from the gravitational wave. That means these two waves have been traveling along parallel to each other for 130 million years. And that tells you that the velocity of gravitational waves and the velocity of light is the same to better than apart in 10 to the 15. It's an enormously important measurement. It's just exactly what Einstein guessed. He assumed that they were the velocity of light. There are many, many crazy crackpot theories of gravity where velocity of gravity waves are not the velocity of light. Well, it turns out they're just wrong. So this was an important event for everybody. And other things came of it that were not quite so fundamental. Here's what this thing is alleged to have looked like if you had been there. Here are the two neutron stars, and they form a new black hole. And in the region in here, they then make a new region that is full of neutrons. And they have, for example, just as the black hole forms, there's a jet, which you see in many black holes, and shock fronts coming out. But also there's something called a kilonova, which is just endless radiation of particles moving almost at 1/10 to 1/3 the velocity of light, colliding with each other, and they're making new nuclei. And neutrons are being added to nuclei. This is a place where nuclear physics is really taking place. And that was something that had been guessed. And in fact, what came of it is sort of remarkable. We now know something which we didn't know for sure. And that is this, many of you will recognize this picture as the periodic table. And there's a different thing in this periodic table than the ones you're familiar with. The colors tell you what is the origin of that particular element. So for example, here's hydrogen, and here's Big Bang fusion, meaning that this hydrogen, much of hydrogen, almost all the hydrogen in the universe, was made at the beginning of, well, at the end of the what we call the radiation phase of the universe. In other words, the universe has formed about 300,000 years before this, but it has been busy near the end when it cooled enough so that hydrogen could be made, namely a proton and an electron could stick together without being torn apart by the radiation. That was where most of the hydrogen was made, sort of 300,000 years, and it comes as a product of the expansion of the universe. A little bit of hydrogen is also made in stars, but it's tiny compared to this. You can see that most of the stuff we know and is important to us does not come out of the Big Bang. In other words, a little bit of lithium, that's about the last, a tiny, tiny amount of beryllium, and then no more. So most of the rest of the periodic table, as you can see, is made inside of supernova or slowly dying stars, green and yellow. And by the way, over here is helium, and all the helium we know about, most of that was made in the Big Bang too. But some of it was made, as you can see, a little bit of it was made in the stars. And so the big discovery then that came of this was people had wondered where the heavy elements come from. In other words, where do things like gold and platinum and silver, for example, things people cherish, or all these rare earths, where do they come from? They don't get cooked up in stars easily. They don't last long enough. And there's not enough neutrons in stars. So it turns out that people had already guessed about 20 years ago that if neutron stars did collide, they would make these heavy elements. And that's what we also saw. People saw that in the spectra of the dying light. Once people saw this with ordinary telescopes, they watched it for weeks and months after, and they saw a particular distribution of light coming out, which was, I wish it had been better than what I'm about to tell you. I wish they had actually seen the spectral lines from these elements, but things are moving so fast that the Doppler shifts of those lines have been broadened, so they couldn't do that. But they did the best they could. They made models of the neutron fluid, and they saw that all the heavies had plenty of time to be made in that process called the R process, where the neutrons keep attaching themselves to an existing nucleus. So now we know, and we're pretty sure, that all the heavy elements that are the purple things in here are things that were made in neutron-star collisions. And that was, I think, a big discovery also. And another nice thing that came of this is a little more subtle. That from the same measurement, I don't know how many of you are aware of that there is a little bit of a controversy now in what is the Hubble constant, namely the rate at which the universe expands as a function of distance away from each other. In other words, difference from the Earth, if you want. Everything is moving away from everything else. And it turns out there is a velocity that people interpret as a velocity, which has caused the redshift of the stars. And that was first discovered by Hubble back in the 20s of the last century. But people now have gotten this down to a very, very good way of doing it. They use supernova in many different galaxies all the way out to, as far as you can see, and they measure the redshift, And then they try very carefully to know the distance to that supernova, and that's called the cosmic distance scale. And they try their very best to measure that. And that's one way that this is measured. And and that's this green. No. No. That's the orange one. Okay. It turns out you can also do this by using the cosmic background radiation, the distribution of the radiation, and these what's called acoustic peaks that are in the radiation, and get the relationship between the size of the universe and the velocity of expansion. And that gives this this green thing. And it turns out you can use the neutron star as a way of being a good standard object, because you have the Einstein equations. You can calculate how strong the gravitational wave strain should be. You know the distance because you've measured that by other means. And so you have a standard object, namely the oscillation of the two neutron stars, that long chirp you heard. And you can use that chirp to give you a relationship between the distance and the velocity. And that is this blue curve here. So without doing anything with a cosmic distance scale, it's not as good. It peaks between these. That's an accident, these two methods. But the point is, this says to the future that if you do enough of these, and which will be the case eventually, you will be able to, by another method, namely the method of looking at gravitational waves, be able to determine the Hubble constant again, and maybe able to settle why there is a controversy between these two very good measurements otherwise. So that's another thing that came out of that wonderful thing. Here's some things which did not come out of it, but people expect will come eventually. And that is, it's best described by this picture here. That chirp, which is shown on the bottom, has a perturbation to it, because into two neutron stars, when they get close together, begin to distort each other gravitationally. And that makes the chirp go at a different rate than the Einstein field equations would say. The Einstein field equations would say, or the chirp, that's the black one down here, is that is a point source. It doesn't have a volume to it. And so now if you include this distortion, what it does is it speeds up the in spiral. And here are various estimates. We didn't get a good number for that, but it's what people are trying to do is trying to figure out how squishy, what is the equation of state of the nuclear matter that's inside this neutron star. And you can get that, at least how easy it is to distort that neutron star from gravitational waves. So that's a thing for the future. Here's another thing for the future. And this may very well happen even before we build the things I'm about to tell you about. This is that when you merge these two stars, this is back to neutron stars, this neutron fluid lives for long enough so it has normal modes that radiate gravitational waves. And here are some of the oscillation frequencies are up in the kilohertz. And here are lines that show the spectra, and then some lines in there showing the detectability in this kind of spectrum. Could we detect that with advanced LIGO? We might. And here's one of the other more advanced detectors who will certainly detect that. So all of that is in the future. Namely, what are the normal modes of even higher density nuclear material than what goes on inside of a neutron star? That's in front of us. And so I'm almost near the end. Here is some of the future, not all of it, in this picture. This picture shows you where we were in advanced. This is, again, strain, spectral density versus the frequency. And here is the spectrum that's associated with what we've been talking about, LIGO. We're not at that time, and that was, we were not yet at what is the design sensitivity of LIGO. I won't go into the reasons for that unless you ask me, but there's still flaws in the apparatus. We're fixing them as we go along. And here is what our next big project will be in LIGO, which uses quantum limited, everything is going to, sensitivity of the system is becoming quantum limited at high frequencies and quantum limited at low frequencies. So this is beginning to be a very fancy detector. And that's what's going to be going on in LIGO by the 1920, oh no, by 2023, 4, 5. And then we're thinking, as the Europeans are also, of building a much larger LIGO. In fact, we call it the Cosmic Explorer. We're busy thinking about that and thinking about it very hard, which will have 40-kilometer arms, 40, not 4-kilometer arms. And it will have different stages. And you can see this is a huge difference in sensitivity, factors of 10, maybe a little more. This is a second version of that detector. And we're thinking that this may happen if we're lucky and we do our designs properly and we do the politics well. That might happen in the sort of early 2030s. But if it does happen, this picture on the right here shows you what is the impact of that. It shows you, it's a cute little picture. It shows you in white the distribution of black holes as we know them as a function of redshift, or this is a function away from the dense, how far you are away from the Earth. This is the furthest away, this is closest. And you'll notice drawn into that are lines for the various detectors. Like the blue line is for where we were in the last runs. A+ is the green one. So we're seeing an awful lot more of the black hole population. Here is the population of neutron star binaries. Well, we're picking up a few, as you see. We get maybe two a year, something like that. Here we're getting sort of now one a week. But here, this is what A+, that's the fancy one there, will do. It still won't get us. So that's part of the reason for going down in here, to try to get more of the neutron stars. And by the time you get to the bottom of this, you have encapsulated the entire population of neutron stars that we think are out in the universe. So that's a picture of where this development might go. It also gets the field into cosmology. And this is the last slide. This tells you, sort of gives you an overview of different things that are going on right now. And this is what this is, a different formulation. This is H, this is the strain, but it's an average strain. So very big factors of 10 differences between these. And here it's the frequency of the gravitational wave. It runs all the way from one end of the piano all the way up to the age of the universe, okay? And here are the different projects. This is the one we've been talking about, ground-based interferometers. And I've told you a little bit about the future for them. But what's also being worked on is a space-based interferometer. And that's almost as old as LIGO. Well, and it's older than LIGO in terms of being thought about by big money. And this started in the 70s. LIGO started in the early 70s being thought about, but it really began in about the 90s. This project has been thought about since the early 70s, no, end of the 70s. And what it is to take 3 satellites, put them in this orbit that you see. Here's the sun, and it's in Earth orbit around the sun. It's at the Lagrange point, and measure the separation of the 3 masses in those satellites. And these allow you to have very much lower frequencies, and that's why it's in this band. And the kind of things you'll see in there are massive black holes, the ones like the collisions of black holes like the one that's in the center of our galaxy, 10 to the 6 solar masses with 10 to the 5 solar masses, enormous collisions, which will go for very, very long times. And then very small objects, small black holes going into into these big ones. It'll also see a lot of white dwarf binaries. These are stars that are not in any way very special. What they are is they're electron degenerate stars. That's probably special, but nevertheless, they're not these enormously, they weigh maybe a little bit more than the sun does, but they're all over our galaxy. So you will see a few of these very close to us, and they will have very strong signals. So this is a thing we're looking at for all sorts of very much more bigger black holes than we are, and very exquisite tests of general relativity. We hope that this will fly as the European mission now with American contributions by about 2030. This is going on right now. This is using pulsars And these are massive, these are pulsars that are all over our galaxy. And generally pulsars that are old pulsars that have been spun up again by their accretion disks. And those make very good clocks. The young pulsars are not very regular in how they spin. And so consequently, you want old pulsars, which are as good as our atomic clocks or even better. And you'd use the distribution of them all over our galaxy and look at how a gravitational wave distorts the timing of the pulsars as it distorts the timing on the Earth. And if you can think of it as the gravitational waves going through our galaxy, they hit a pulsar and accelerate it away in some direction. That causes a Doppler shift on the pulsar. That gravitational wave a little bit later hits the Earth and accelerates it in another direction. And you can use those accelerations as a way of seeing two Doppler shifts, which are a way of looking at timing changes in the pulse rate of the pulsar. That's one way to think about this. And these tests, they're now probably 50 pulsars that they've been timing for about 10 years at least. And what they will see, and they hope to see, is the coalescence of supermassive black holes, 10 to the 11, 10 to the 12 solar masses. People have seen these in Hubble telescope pictures, but this might see those as discrete signals. But more likely, and that they may be seeing that now, they're worried, not worried about it, they think they may have something of just the isotropic background of all these very much large, gigantic black holes unresolved. Unresolved, this is just going on everywhere in the universe, and you haven't picked out the individual pulse, you haven't picked out the individual waveforms, you superpose them, and you get a background noise. And they think that that's something they can see. They may even be seeing it now. And the signals here are all in periods of years, okay? And the last thing is something which is all thought that people who are doing this thought they had seen gravitational waves, but this is going on with a vengeance right now. And at least 5 groups in the world doing measurements of the cosmic background polarization. That means the direction of the electric field in the cosmic background. And you can, from that, if there are primordial gravitational waves that might have come from inflation, or even from phase transitions in the early universe, but more likely the inflation. And these waves would have caused density fluctuations in the plasma that has made the cosmic background. But they're density fluctuations that look very much more like the distribution of gravitational wave densities. In other words, you take that quadrupole pattern and impose that on different parts of the universe, and you will see a particular pattern of polarization. The polarization vectors will be doing something called B modes, and they're shown in this picture. And there are, of course, other things that polarize the cosmic background. For example, just temperature fluctuations, and they're all over the place. And so consequently, the temperature fluctuations are huge. They might be 10 to the minus 5 Kelvin. In other words, if I express it in terms of a temperature, whereas the cosmic background is about 2.7 Kelvin as a signal, the amplitude of the temperature fluctuations is about 10 to the minus, it's 10 microkelvin. And the fluctuations in due to the gravitational waves are maybe, if you're lucky, 10 nanokelvin. So it's a very hard experiment. But the people, and they have to be careful, make sure not looking at dust. But people all over the world are looking at people from the Chile, especially in South America. There's a wonderful experiment in the Atacama Desert, which in fact there's a whole group of people there doing this. And then there are people in Chile. And then there are a group of people in the South Pole. And there are now people in Tibet doing this experiment as well. So that has a chance of seeing gravitational waves from a primordial background. It's a very exciting experiment. None of these other experiments, LIGO can't do it. LISA, this thing here, can't look for that comes from inflation. This is never sensitive enough to do it. So it's this, and there is an experiment. I won't go into it. You can look it up if you like. It's called Big Bang Observer. And what that comes down to is trying to do this in space. And it's the combination of what the techniques used on the ground with the techniques used in space and melding them together, putting that experiment into space could get you the sensitivity to measure the primordial gravitational radiation from inflation directly. So good. Thank you very much.
Thank you very much, Professor Weiner.
Yeah.
Weiner. It was very, very, very interesting your talk, and I can tell you that YouTube is full of questions, so we are going to have to select a little bit to give you all the questions. But we are super happy for your talk and on the brightest future of the gravitational wave astronomy that is coming, and what we are going to learn now with the new result and everything. So first of all, I would like to comment to the people that is following us in YouTube and following us for all these years in the channel, that we are super happy that you have been here supporting the project. And of course, to all the speakers of the previous webinars that we have had, and of course also the coordinators. That in this special occasion we have invited the previous coordinator of the webinars that are also here part of the project. I mean of the Zoom session, and of course. As we proceed every time in the webinar, we are going to start with some questions for you, Professor Reiner. And after that, we're going to have some questions from the people here in the Zoom, and of course, to all the people that is following in YouTube or either in our social network, that you can subscribe and follow to keep updated with the latest news about the webinar that we are going to have in the future. So let's start with one of the questions that we have from YouTube. Let me just to look it. And Nissan Khan, he is asking about from the beginning of your talk, what is the uncertainty in the measurement of delta L? If you can comment on that.
Yeah, and the uncertainty in measurement is the calibration of the detectors. In other words, right now, I mean, in fact, it's very important to have that calibration right, because that's how you can measure the distance to the star. And right now, it's a frequency-dependent statement. In other words, I'll give you some numbers, but it's not the same at all frequencies, at gravitational wave frequencies. We think we can do sort of 1 to 2% at low frequencies, but we cannot do that well at, by that I mean at 100 hertz, 20 hertz to 100 hertz, maybe 200 hertz. At higher frequencies, there are effects of the bending of the masses and stuff like that. And I think the numbers are not better than about 3 or 4%. Okay.
Okay, thank you. We have now a little, I mean, not a little question, but a question from the people here in the Zoom session. That is Jorge Diaz. Jorge, can you open your microphone for the question, please?
Yeah, I hope you can hear me.
Good, I can hear you well, yeah.
Great. Yeah, you're the one that matters. Thanks for that very nice overview. It was great. In the winter of 2016, I was teaching general relativity to grad students. So it was perfect timing for me when I picked the gravitational wave as one of the clear examples on how to derive the wave equation and the solution. So I have a question regarding the solution of the gravitational wave equation. You show one of these diagrams when you show the oscillation, one of these modes. So we have these so-called plus modes and the X modes.
Right.
Is there any way that in LIGO...
No, wait a minute, you're talking about the gravitational wave. The
yeah,
plus
talking about
the polarization of the wave is what you're talking about.
The polarization, exactly.
Yeah, of the wave. I only didn't mention that, but go ahead, keep going.
Well, in this diagram, you could sort of infer that that would be somehow the plus polarization.
Yeah, go ahead.
The question I have is there any way that any of these gravitational wave detectors can tell us something about these polarization modes? And what could we learn by measuring that?
In fact, thank you for that question. I've left that out, and I'm kind of feel embarrassed that I left it out. What you're referring to is actually something that Einstein knew right away when he did this. There are two, like in electromagnetic waves, there are polarizations. For two polarizations, either you can do it both circular or linear. But with gravitation waves, it turns out there are two polarizations as well. And they are either when something is like you were doing with your, I guess like, yeah, I can do that over here. It's like this. And if you turn that picture by 45 degrees, that polarization is perpendicular, it's orthogonal to the polarization. And you are absolutely right. In order to really unscramble what's going on at the source, to understand the dynamics of the source, you have to measure both polarizations. So when you taught general relativity and you said the boys have to know both of those polarizations, you were right. And I left that out. Now, that's one of the arguments. Let me tell you what, we had to make a decision. And you can see how experimenters are sometimes forced into decisions. We had to make a decision whether we should make the initial LIGO sensitive to polarization or not. And what we did is we decided that we would orient the two detectors in the United States in such a way that they would be insensitive to polarization. They would only measure the same polarization. And the reason was we were so worried about missing a signal. Okay. Right. Now that we know there's a field there, I mean, we're encouraging everybody who builds detectors, and we're doing, and those triangles, by the way, that you see that are made in LISA, we'll measure all the polarizations. And we also get the polarization now from having Virgo at a completely different angle with respect to the other two detectors. So we now do get the polarization, okay? We measured, so and that data analysis has to include the polarization. Now, let me tell you the unfortunate fact. It would work a hell of a lot better if all the detectors had the same sensitivity. And that isn't the case at this moment. At this moment, unfortunately, the Virgo system, because it's shorter and also they're working on it, is not as sensitive. So you don't get a solution for the two polarizations to the same precision you would have had if all three detectors had the same sensitivity. And that will be solved in the future. For example, the Europeans are thinking of building something called the Einstein telescope, which I should have mentioned in my talk. But that's something also that is a third generation detector, and that's built in the shape of a triangle. And that it gives you internal consistency so that you can measure the polarization. Okay, so yes, you're absolutely right. We should do better. We will do better. Okay.
Great. Good luck. Thank you.
Okay, thank you, Jorge. So we have also another question from one of the guys here in the Zoom, Germán. He asked
Hi. Thank you very much, Professor, for this very nice talk. My question is, well, I think more political. It's about these new projects or the future that you were mentioning, huge projects. Indeed, well, LIGO is a huge project and needs a lot of money and a lot of negotiation with politicians, and it strongly relies on public money. But we have seen in recent times that also private are getting involved, for example, in space exploration with SpaceX, but not only for commercial purposes, but also for exploring Mars. There's some, I don't know if negotiations or ideas about to get involved private funds or ways to not only use public money, but also to get involved with private companies that can help build this new project for gravitational waves?
Well, that's an interesting question. Thank you for that. This business of having large amounts of private money going into research has an old tradition, and then it went to hell. I don't know if you know how it happened in the United States. It was that way back at the turn of the century of the 1900s. The 1800s to the 1900s, people like Andrew Carnegie, the people who had made so much money and felt guilty about it, gave it back to the public. And they did it in large quantities for those days. Then business got very much more greedy after a while, and smaller businesses. And it's only in the last probably 30 years, the Rockefeller Foundation has supported that. They're big enough to do it. But only in the last 20 or 30 years has it been that many more businesses are now thinking about putting money into research. And much of it is as an honorary thing, like the fact that they'd like to make science progress, not trying to make money for themselves, because, what kind of money can you make out of a gravitational wave detector or out of a telescope? So it turns out what you're saying is something which may be possible again. There are now, in fact, there's a whole bunch of people trying to be the liaison between people who have a lot of money in industry and people who are scientists who are trying to figure how to make big projects go. I'll give you a good example of that. The two telescopes are going to go in the, I don't know if it's on the Atacama, it's in Chile, the 30-meter telescope. That one of the 30-meter telescopes is going to go there. Another one may go into Hawaii. That is mostly done on private money. Okay. Alma, well, not Alma, but anyway, those are the best examples. We're looking at that a little bit. The company there are now foundations that will look at this, but you have to be careful. They have to feel, and this is what, there is a piece of ego involved in it. The industry or the people who want to give the money want to make sure that it is sufficiently something that they can be identified with, that they get a humanitarian response for it. In other words, what I'm trying to say is that they get recognition for having done that. So generally that means naming the thing after the people. That's one thing. That's fine. That's no big deal. But then the thing has to be sufficiently unique that it makes a big splash. In other words, now maybe the very first gravitational experiment could have been done that way, but now gravitational wave radiation is becoming more a matter of, it's part of the science. It's been accepted. You know, I mean, not that we shouldn't try. Look, I'm not arguing against the idea. I'll tell you what we're trying to do in the United States is we're trying to see how we can get multiple states to do this together. In other words, or multiple even agencies within one country. For example, the Department of Energy now has a lot of interest in what's called fundamental physics. And gravitation, because of the fact that it says things about dark matter, it'll say something about dark energy, about what is the fundamental science behind gravitation. That becomes interesting to the scientific part of the Department of Energy, not just the scientific part of that, not just the National Science Foundation. So what you're saying is we should look a little more hard if we want to get this going. And we're trying to see how to do it. Right now, our biggest problem is, tell you what I'm working on a lot, is how to make it cheaper so you can afford it. That, as an engineer and a scientist, to me, that's the most important thing. Right now, one of these third generation detectors that I'm telling you about could cost, it doesn't have to, but it could cost around $1 billion, 10 to the $9. That's that's pretty big. You know, LIGO itself, of course, has cost about that much over 20 years when you include the operating and everything else, but not as a single expense. So I don't know how to answer you. You're asking me, why don't we go after private money? Well, we'll try it if we can't succeed the other way. Okay. Yeah.
Thank you very much.
Yeah, sure.
Thank you, Herman, for the question. So let me just again to go some questions in YouTube. And the next questions, because are two that are related, it's the same person that asked, is the Joseph Pradler. He's asking to you first if you can comment about the nanograph result, if you have any comments on that. And also he's asking how long will it take to get the statistic to measure the Hubble with a percentage accuracy to help to resolve the Hubble.
That's a good question. Both of them. Well, I can quickly tell you, you can look this up yourself on the archive. The results from, it's called the nanograph 12.5 year results. And I can tell you what they're saying. They're saying that they have a spectrum in 45 or 47 pulsars that they have measured over 12 years that would be appropriate to be one from large black holes colliding with each other. And they see that in all of those stars. On the other hand, they don't see something which is absolutely critical to making sure that it's gravitational waves. And that is that, and that has to do with the geometry of that experiment. This was done by Hellings. You can look up Hellings, and I've forgotten the other author. They came up with a way of, if you correlate the amount of frequency shift of the pulsars, depending where they are in the galaxy, you should see some of them make a like a quadrupolar pattern. And what will be that some of them in pairs will look like they've increased their frequencies, and others will look like they've decreased their frequencies. And that's a very definite pattern on the sky. And that pattern has not been observed. Okay. So that's the best I can tell you. You can look it up yourself. It's on the archive, and it's there probably about a month, something like that. Okay. Now, the idea of how well can you do with the Hubble constant, or even the dark energy, the equation of state of dark energy by using, it's never going to be as good as you can do with optics. In other words, we estimate that it will be good enough possibly to separate something of the order of a few percent. And it won't be 1%, we don't think, but we're not sure of that. It depends if we're lucky. It depends, I'll tell you what it really depends on. If there is some feature in the spectrum of the black hole binary mass distribution, if the binary black hole mass distribution, if that has a feature to it, which allows you to solve for the distance independent of the redshift from the waveform, then it could go very much better. But that hasn't yet, we're still assuming that the spectrum has no holes in it, that's uniform in the mass distribution. But if that changes as we learn more, we might get down to 1%. Look, I'm making that up a little bit. There are people who have really studied this. It's never going to be the precision. It's going to be something which says, is the cosmological version of the Hubble constant or the near version of the cosmological constant. In other words, let me tell you what those are. The cosmological one is the one you get from the acoustic modes of the CMB, and the near one you get from the supernova. Are they different because of something which has been left out in the two? And that's something I think we can settle. Okay. But I can't tell you the precision yet. If the black holes have a special feature in their mass spectrum, I'm very much more optimistic. Yeah.
Okay, thank you, Professor Rai.
Yeah.
We have one question. I mean, two more questions, because also we cannot be here forever. But Camilo Garcia Celi, if he wanted to address you with a question. Camilo, if you can unmute yourself. Yeah.
Yeah, thank you very much for the talk. Actually, I was going to ask about nanograph. The question was already answered.
Okay.
Thank you.
So we save the time. No, yeah. Let's continue just with Joel Jones. He's one of the coordinators here. He wants also to ask some question.
Okay. Sorry, we repeat what you said.
No, sorry. So it's my turn to ask a question. So this is a slightly technical question, maybe, because you mentioned that you're measuring the strain, but on the plots you show the strain in units of 1/√² of hertz, right? So how does that work out?
Okay. When you plot in time, you plot the function itself, h of t. Okay, h of t. How does the time vary? How does it h vary in time? We can always that's how we measure it, but it's much easier for us to understand what's wrong with the apparatus, and we measure all the time the noise in the apparatus. And what we're comparing, that's why what you want to do is you want to convert that time series into a power spectrum. In other words, take the Fourier transform, take the Fourier transform of the time series, multiply it by its conjugate, and you get something called h² of f. That's the amount of energy in the spectrum of h at each frequency. That's per hertz. Amount of h per bandwidth hertz. Now, if you want to make something linear, you take the square root of that. So it's the amplitude of the power spectrum. I'm sorry and so if you want to get h out of that, I should have showed you that. What you do is you go to those pictures and just look in a region and take the square root of the frequency and multiply it by what the y-axis says. And you will get, it's a pretty good approximation, what value of H, RMS, we can measure at that frequency. Okay? So go to that, for example, at 1 kilohertz, suppose you're interested in. I don't know, I've forgotten the number. I think it says 10 to the minus 22 strain per root hertz, something like that. You look at 100 hertz, take the square root of 100, that's 10. So it turns out that's 10 to the minus 22 times 10, which is about 10 to the minus 21, okay, at 100 hertz. I'll tell you why we do it. It's for us, not for you.
Right. I imagine it was related to the first question regarding the uncertainty, and then you mentioned this thing about the depending, or that it depended on the frequency that you were measuring.
Yeah, well, I'll tell you that's a separate issue. How does the calibration depend on the frequency? And that has to do with, I'll tell you exactly how that happens. You might enjoy this. We push the mass with photons. We calibrate the motion of the mass by putting separate laser light onto the mass in pulses. And we watch how it moves. And we know how much power is in that light. And that's how we establish the sensitivity of the apparatus. We know we have moved the mass by a certain amount. How much signal was there at the output of the interferometer? It's a way of pushing. I'm sorry, there's some noise here. We'll have to wait for them to go. Yeah, here we go. You have to push with a known amount of push. And that's what another laser does. So it turns out when you do that, the mass bends a little bit. The mass itself, these gigantic masses, bend at the scale that we're measuring a little bit. And that happens at higher frequencies. And that's why we have an uncertainty. Okay, it's a detail. Okay.
Thank you very much.
Yeah.
Okay, so we have a couple of more questions, and then we will finish the webinar. It was super interesting. So we have one question that is from, I lost it, from Maria Kikeli. She's asking, how do we know that the current data aren't by two waves that are interfering?
You mean two gravitational waves that are interfering?
Gravitational wave interfering.
Well, I had not contemplated that. I mean, it's kind of a rare event, but I'll tell you where I'll tell you where we might have to start worrying about that is when you look at a stochastic background that's coming from all directions. And then you have to look, and that problem has been worked out. You have many waves hitting the mass simultaneously. And then you have to do it as a power spectrum. That's how you do it. Yeah.
Okay, so now we have the last question from Alejandro Avendaño, Cardenas Avendaño, that is here. Alejandro, please, if you want to ask.
Thank you, Roberto. Thank you, Professor Weiss, for this nice talk. I'm always asking this type of questions because they always appear on our YouTube channel. And in particular, it came up this one, which is like, it's impossible to catch up or to keep up with many papers coming about different interesting topics that are happening at the moment. So people constantly ask us, and in particular, people in Latin America, how would you give advice on entering a field like this that is happening at the moment? So keeping in mind that it's a topic that is changing rapidly, and like many people are on top of it. So what would be your advice to early career scientists?
I see what you're saying. Okay. Yeah. Well, I mean, there are many ways to answer that. I mean, if you're talking about a person who's an undergraduate in college and interested enough, I would try to go to graduate school in a place where they do this. And there are many places that do that. If you're a professional already in the, you're, let's say, a postdoc or something like that. Again, I mean, it's the best thing to do is to try to work with the people who are in it. But the place where if you're really interested in this particular field, almost everybody publishes first on the archive. And that's what you'll notice, that if you're trying to keep up with what's going on, you can use the archive as a way of indexing You know, for example, you look up under astrophysics, gravity. My God, you will get all the papers that have, some of them wrong, some of them not been, you know, some of them not right, but you can keep up with that way. That's probably the best I can recommend to you. Yeah.
Thank you.
Okay, so I guess we are done with the question. I mean, there are many questions for you, Professor Weiss, and also there are a lot of congratulations to you for your nice talk. But unfortunately, we have the time restriction. We cannot be here forever.
So do you need more of me now? No. Okay. Should I go have lunch?
Yeah, I mean, yes. Just let me just wrap up, just to thank to all the people that is following. To thank you to you for the webinar. Also, we are here in Chile. I mean, where I am, Chile is lunchtime, so we are all here. No, but yeah, but it's the science. It's nice to listen to good science. So
well, you've got a good bunch of people there. I have to tell you, those are good questions. I'm very glad I did this. Okay, and congratulations to you for a very clever idea of this LAW. I think it's smart.
Well, thank you very much.
Thank you. Okay, I'm gonna leave you guys.
Okay. Just let me to close the transmission in YouTube, and we are all free. So for all the people that is following us in YouTube, please, you can either subscribe to the channel to keep update with the latest webinar that we're gonna keep going in the future, and we can see us again in the next time. Sorry for all the people that we couldn't address the question, but there are so many that we have to select some, but they were very interesting. So see you in the next time, and keep updated with the social networks.
Thank you.
Thank you to all.
Okay.
Okay, now we are offline.
Okay.
Okay, bye-bye.